Assalamu alaikum. Welcome to lecture number 28 of Digital Signal Processing. Up till now we have covered various topics of digital signal processing, including analysis of signals and system in time domain, as well as we have covered design aspect of discrete time system. This week is supposed to be the last week of this recorded series, and during this week we will try to wind up our discussion regarding the frequency domain representation of discrete time system. This week we will learn interesting things about how we can design or analyze any discrete time system with the help of its frequency domain representation. Hope you remember the lectures of previous week in which we have discussed how we can design discrete time system. Although we have designed some discrete time systems in based upon finite impulse response, but for infinite impulse response system we concluded that we need some mathematical tools to design these systems, as the design of this system is not an easy task, and we also concluded that for this we need to learn about Z transform. So basically the frequency domain representation aspect of a discrete time system is covered in this week, and we will also relate how the discrete time system can be related to analog systems and how we can transform the representation of analog system to discrete time system. It means that if the response is given to us in analog domain, how we can design a discrete time system with the same response. So this week we will try to cover these aspects of discrete time system designing as well as analyzing. In this lecture, we are going to learn the relationship between Laplace transform and Fourier transform, the stability region in S-plane, which is the graphical representation of Laplace transform, and we try to understand how we can calculate frequency response with the help of pole zero constellation. In this slide, we are going to learn the mathematical relationship between Laplace transform and Fourier transform. Although we know that Fourier transform give us only the frequency response, but Laplace transform give us two types of information. First one is the frequency response of the system, and the second one is regarding the stability of the system. So we can say that Fourier transform is a subset of Laplace transform, but this is the qualitative statement. But in this slide we are going to prove this statement quantitatively with the help of some mathematical relationships. As we all know that the Laplace transform is given by this mathematical expression. This expression is used when we want to transform any signal into S-plane or S-domain, because we know that Laplace transform the signal into S-plane, and S-plane is basically a graphical representation of the frequency response as well as stability of the system. Actually, it is a 3D plot and can be drawn in 2 dimensions and the dimension of this S-plane are stability and the frequency. If we want to plot the third dimension, then it is gain of the frequency. However, for our easiness, we mostly plot S-plane in 2 dimensions. So this expression is basically used to transform any signal which is analog in nature to Laplace domain or S domain. And if we want to explore this S, then this S is basically complex frequency, which is the combination of two terms. First one is sigma, which is the stability of the system, and second one is omega, which is the frequency of the system or radiant frequency of the system. And J is just telling us that these two parameters are orthogonal to each other. So we just expanded the term complex frequency S by sigma plus j omega. Further simplifying this expression, we are separating out the terms sigma and j omega in a fashion e raised to power sigma t into e raised to power minus j omega t. Yes, we can do this simplification because when we combine this basis function again, it will turn back to this expression, which is sigma plus j omega. But we know that the Fourier transform only tells us regarding the frequency response of the system. It does not tell us the stability of the system. Or in other words, what happens if we put sigma is equal to 0 in this expression? Simply, when we put sigma is equal to 0 in this expression, then this expression is turned to this. And in this expression, you know that e raised to power 0 is always 1. So the expression is simplified to integral minus infinity to infinity x of t, and the basis function is e raised to power minus j omega t, and this function is obtained when we assumed sigma is equal to 0. At this stage, actually we supposed that if we put sigma is equal to 0 in this equation, what will happen? And we ended up with this final expression. In this final expression, you can notice that we have an integral sign which is denoting the analog domain or continuous time signal, and you can also see the limit, which is minus infinity to infinity, means we have infinite values which we have to integrate to obtain the answer. And the expression of the signal is represented by x of t. This means this is a continuous time signal. So actually this signal is basically the response of the system for which we are going to determine the frequency response as well as its stability. So this is basically a continuous time signal. Integral again is used for continuous or infinite values, and it is also supported by the limit of integral, which is minus infinity to infinity. And here is the basis function. So this is the final expression we obtained when we put sigma is equal to 0 in the mathematical expression of Laplace transform. But it is very interesting to note that the final expression, this one is actually the expression of continuous time Fourier transform. If you look back at the lectures of CTFT and try to match up the equation, then this expression is actually similar to the expression of continuous time Fourier transform, which is CTFT. So we started with the Laplace transform and ended up with the equation of Fourier transform. And this is basically the relationship between these two transform, that these two transform are equal at sigma is equal to 0, which we already stated in qualitative terms, that Fourier transform only tells us about the frequency response, but Laplace transform tells us about stability as well as frequency response of the system, which we proved with this mathematical procedure. So here we can say that we have proved it mathematically, that Fourier transform is a subset of Laplace transform for sigma is equal to 0. Because in Fourier transform we are not interested in stability, we are only interested in the frequency response of the system. So here we can say that Fourier transform tells us 50% of the information which is provided by Laplace transform. Keeping in mind that Laplace transform deals with the analysis of systems which are analog in nature, so this expression is basically used to analyze analog system. So if we are interested to analyze any discrete time system, we cannot use Laplace transform. For that we have another transform which is known as Z transform. Now we are more interested to determine the stability of any system. As you know that Laplace transform is used to analyze any analog system, so we must know by looking at the graphical representation of S-plane whether this system is stable or not. So we will use this information to determine the stability of a discrete time system. But here we first learn regarding the stability region in S-plane, which belongs to the Laplace transform. And you all know that Laplace transform deals with the analog systems. So in this slide we are going to learn that by looking at the graphical representation of analog system, how one can determine its stability. So basically in S-plane we have different poles and zeros lie on different regions. Basically, to understand poles and zeros of the system, we first understand regarding the transfer function. As you all know, the transfer function of any system is the frequency dependent ratio of output over input. You can say that transfer function is generally the ratio of output over input, or in easier term we can say transfer function can be expressed in terms of its numerator polynomial and denominator polynomial. So if we cancel out the similar terms in numerator and denominator, we will ended up with the simplified expression. So the roots of a numerator are termed as zeros of the system and are usually represented by circle in the graphical representation, and we usually denote 0 by z. Similarly, roots of the denominator are poles of the system, and they are represented by cross sign, and it is denoted by p. For example, if there are two poles in the system, then we denote it by p1 and p2 respectively, and in the graphical format we represent it with the cross sign. So remember this thing, we have a transfer function. Transfer function is basically the ratio of output over input, and we can express this transfer function in simplified form because it may be possible that some numerator terms cancel out with some denominator term. So after simplification we get some expression in the form of numerator and denominator polynomial, and in this polynomial the roots of numerator are termed as zeros and the roots of a denominator are termed as poles. Now it is very interesting to know that why we are calling the roots of a numerator as zeros of the system and why we are calling the roots of a denominator as poles of the system. It is because the 0, which is the root of the numerator polynomial, is that value which results in 0 value of the function. In easier term, you can understand this by the concept: if we put the same magnitude which is calculated to be the 0 of the system, the entire transfer function reduced to 0. So basically 0 as the root of a numerator polynomial is that value which results in a 0 value of the function. Similarly, what about pole? Pole is a value for which the function becomes infinite. That's why we are calling it as pole. So if we apply the same frequency as 0 or pole, what will happen with the function? So assume we are applying the frequency which is equal to the 0 of the function or 0 of the system. Then what happen with the transfer function? Whole transfer function will reduce to 0. That's why we are calling this particular frequency as the 0 of the system. And if we apply the frequency which is equal to the pole of the system, the response of the system at that particular frequency will turn up to infinite value. That's why we are calling this particular frequency or this particular root of this system as the pole of the system. So this is the basic discussion about poles and zeros of this system, which helps us in determine the stability region in S plane or in Z plane as well, because they are the basic building block to represent our system response graphically. Another interesting thing I want to add here related to zeros and pole and its relationship with the stability of any system is that only poles contribute towards the stability of any system. Zeros has no role in determining the stability of any system. Here you can see this is the transfer function, this one is the numerator polynomial, this one is the denominator polynomial. Zeros is represented by a circle and pole is represented by a cross sign. And graphical representation of S-plane is basically this. You can see sigma is taken on x-axis and omega is taken on y-axis, and poles and zeros are plotted randomly. This is basically a random representation of any system, just to tell you that in this way zeros and poles are plotted on this entire region. You can plot this pole anywhere and this zero anywhere. So this is basically the entire region of S-plane, and zeros and poles of the system lie anywhere in the entire region, starting from minus infinity to plus infinity along x-axis, as well as minus infinity to positive infinity along the y-axis. So these zeros and poles can spread anywhere. But what about the stability region in S-plane? Whether the entire plane is stable or there is some particular quadrant or region in which the system shows a stable response. So we will see it in the next slide. So here you can see it is the standard mathematical representation of Laplace transform, which can be elaborated as sigma plus j omega, as s can be expanded into sigma plus j omega. S is basically a complex frequency which is expanded to sigma and j omega. And the stability region in S-plane lie when sigma is less than or equal to 0, which means sigma can vary from minus infinity to 0 to make this system stable. If sigma value become positive, which is beyond this range, then our system will behave unstably, or we can say that this type of system is unstable. So it means that in the S-plane, the region of stability lies in the left hand side. If any of the pole lie on the right hand side of the S-plane, then our system will become unstable. As we now understand regarding the S-plane and pole zero configuration in S-plane, as well as stability region in the S-plane, now we are going to learn how we can determine the frequency response from pole zero constellation. Here you can see you have a transfer function which is represented by numerator and denominator polynomial, and from this generic expression you can extract the value of zeros and poles of the system if some specific expression is given to you. For our easiness, we consider some generic cases to understand how our system behave or what will be its frequency response as well as its stability if the poles and zero have certain configuration. So here we are going to learn regarding the frequency response from pole zero constellation. We are first drawing S-plane, and in S-plane you know that we have x-axis marked as sigma and we have y-axis marked as j omega, and we already know that the left hand side of the plane, which is this quadrant highlighted by my pointer, and this quadrant is basically the region in which our system shows stable response, and the region highlighted by pointer, which is basically the left hand side of the S plane, is basically unstable region, because you can see that here in the right hand side the value of this sigma is positive and the value of sigma remains negative for left hand side of the plane, and we already know that the stability region lie from minus infinity to 0, which is along this axis. So this entire region turns to be the stable region of S-plane. Now if any pole lie in this region, we can say with confidence that this system is stable. But if any pole lie on the right hand side of this S-plane, we can say that this system will behave unstably. So here, as you can see, we have a pole marked as cross sign on the left hand side of the plane. Before calculating anything, we can comment by looking at this pole zero constellation that this system is a stable system. Now we have another zero lie exactly on the same point where we have a pole. So in this way, zeros and pole actually overlap with each other, or you can say that the numerator polynomial cancel out the denominator polynomial. So what kind of frequency response we will obtain in this case? We can easily determine the frequency response from this plot. If we move along y-axis, we will get the frequency response. For example, if we apply these frequencies which are on the y-axis, then this will be the frequency response of this system. So what is the impact of zero and pole? Zero basically attenuates the magnitude and pole basically provide gain to the frequency response. So if we encounter any zero or pole in our walking track along the y-axis, we will shift the frequency response accordingly. For example, if we are walking along this track, which is y-axis, and we encounter a pole here, so what we will do, we will plot frequency response like I have moved the pointer, this one. And what about this side? This one. But as you can see here, a zero is exactly overlapped with the pole, so the effect of pole is cancelled with the zero. It means whatever the gain pole is providing, the same gain is cancelled out by the zero. So there is no effect on the frequency response if we walk along the y-axis. So by looking at this S-plane, we concluded regarding the stability of the system as well as its frequency response. Stability of the system, again I am repeating, is just by looking at the position of the pole. If the pole lie on the left hand side or left hand side of the plane, the system is stable. But if the pole lie on the right hand side, which is this side, the system is unstable. And what about the frequency response? If we walk along the y-axis, we will shift the frequency response according to the pole and zero we face along this walking track. But in this plot, these pole and zero exactly overlap with each other, which means that they are cancelling each other effects. So it means that there is neither poles effect nor zero effect, and we will get a straight line as a frequency response. So if we just plot the frequency response by this pole zero constellation, we have omega or frequency on the x-axis, and along the y-axis we have a magnitude. And as you know that we have a DC response or a straight line along the y-axis here, so this response is basically just the frequency response, and this response can be attained by taking the Fourier transform of that signal. So this is basically the representation of Laplace transform. From Laplace transform, we will comment regarding the stability of the system as well as its frequency response. And this one is basically plotted by taking the Fourier transform of any signal, which is the same result which is obtained from this S-plane. Now we will look at some different and complicated graphical representation of or graphical configuration of poles and zero to understand how the system will behave in that particular configurations. So moving to the next. slide. Here again we have x-axis marked as sigma, y-axis marked as j omega. Now here you can see we have a pole not along the x-axis, but it is lie somewhere as shown in the S-plane, and we have another pole marked here. Now if we have this type of configuration, how we can determine the stability and frequency response of the system? First, to solve regarding the stability of the system, we have to look whether these poles lie in the left hand side or in the right hand side of the S-plane. So by looking at this pole zero constellation, we can easily say that these poles are in the left hand side of the S-plane. None of the poles lie on the right hand plane. So which means that this system is a stable system. Now what about its frequency response? For frequency response, we again have to walk along the y-axis. By the term walking, I mean to say I am varying frequencies which are present on the y-axis and the frequencies at which any pole or zero encounter during varying the frequency, I will shift my response accordingly. So this is basically the response if I move along the y-axis. I am walking along the y-axis, I encounter a pole. It means that I am applying some gain to the frequency response at this particular frequency. Then after some time the effect of zero will reduce and my response will tends again to the normalized value. So my response is again reduced to the normalized value at which I am walking previously. Now again I am walking and again I encounter a pole. So again my frequency response is going to rise at this particular position, and exactly at this frequency my response is at peak position. After crossing this frequency, my response will again reduce to the normalized value, and it is normalized after moving away from this pole. So in this way I plot the frequency response with the help of information of poles and zero in the S-plane. Again I am repeating that these two poles are on the left hand side of the plane, so my system is stable, and to determine the frequency response I have to walk around along the y-axis. So I am walking along the y-axis. If I encounter any pole, I will provide gain to the frequency response such as I provided in this curve, and then I reduce this gain again to the normalized value as I passed this frequency. So the gain is again normalized, and I'm walking on the y-axis. Again I encounter a second pole, so I will again provide some gain to the frequency response, and after particular point, which is exactly the position at which the pole is lying, after that point I will reduce the frequency response gain and it will reduce to the normalized value. So in this way I have plotted the frequency response of the system with the help of pole zero constellation. And the same frequency response we obtained when we apply Fourier transform to this system. Here you can see that we have the same frequency response obtained by the S-plane, but the additional information we are getting from this S-plane is stability of the system.